Examine the architecture of modern electronics, and you will find a specific passive component embedded in nearly every complex circuit board. This is the capacitor. Its core function is to capture and hold electrical energy in place, storing it temporarily as a stationary electric field, rather than allowing it to flow through the circuit. This method of trapping charge dates back to the 18th century, when scientists used Leyden jars, glass containers lined with metal foil, to pool static electricity. The glass acted as an insulator, preventing the opposite charges from reaching each other. The modern version operates on these same principles. By examining the physical geometry of parallel metal plates and the calculus governing how voltage changes over time, we can decode how these components filter noise, protect our delicate microchips, and deliver massive power spikes. A capacitor's ability to manipulate time and frequencies is a direct consequence of raw physical geometry. Regardless of its external shape, every capacitor utilizes a universal internal architecture. Two conductive metal plates placed parallel to one another, separated by an insulating material called a dielectric. When an external voltage is applied, electrons are pushed onto one of the plates. Because they cannot cross the dielectric, they stay there, their presence repelling like charges on the opposite plate and leaving it positively charged. This capacity to store charge is defined by a mathematical relationship. Capacitance increases when you expand the overlapping surface area, A, or when you shrink the physical distance, D, between them. This interaction is modulated by the permittivity of the dielectric. An engineer cannot reprogram a capacitor after it's built. Its energy limit is permanently hard-coded by the physical volume and material chemistry manufactured into it. We measure this storage capacity in farads. 1 farad represents the ability to store 1 coulomb of charge for every 1 volt of electrical potential applied to the plates. In an active circuit, the capacitor's behavior is dictated by the rate of change in voltage over time. Mathematically, the current flowing through a capacitor is the product of its capacitance and that rate of change, or dV over dt. If the voltage is a steady, unchanging DC signal, the rate of change is 0. Consequently, the resulting current through the capacitor is also 0. However, if the voltage rises or falls rapidly, as it does with high-frequency signals, the steep rate of change induces a significant current to flow through the component. This creates a predictable behavior for circuit designers. Capacitors isolate steady DC power while providing a low-impedance path for rapid AC noise. When a circuit requires more energy storage than a single component can provide, engineers wire multiple capacitors together in parallel. In this configuration, you simply add their individual values to find the total capacitance. This works because wiring capacitors in parallel is physically equivalent to merging their internal plates, expanding the total surface area available to store charge. Conversely, placing capacitors in a series line reduces the total circuit capacitance. By forcing the charge to navigate multiple dielectrics in a row, you are effectively increasing the distance between the outermost active plates. Designers use series arrays to divide electrical pressure across multiple components, allowing them to double the maximum safe voltage rating of the entire cluster. Combining capacitors allows designers to manipulate these geometric constraints, effectively hacking the physical limits of individual components to survive extreme circuit conditions. The dielectric material dictates a capacitor specialty. Ceramic capacitors have very low equivalent series resistance, making them ideal for high-frequency applications where heat loss is minimized. When high-capacity bulk storage is needed, engineers use aluminum electrolytic capacitors. These use tightly rolled chemical layers to pack massive capacities into small cylindrical cans. But this chemical architecture comes with a risk. Electrolytic capacitors are polarized, meaning they can only safely handle current flowing in one designated direction. Applying reverse voltage to the cathode causes an internal chemical reaction. The resulting gas pressure builds until the metal casing bulges and eventually bursts open. Designing a reliable circuit requires balancing pure mathematical theory against these volatile physical and chemical realities. This calculus explains why every sensitive integrated circuit on a board is surrounded by tiny capacitors. As a processor cycles through data, it rapidly changes its power requirements. These abrupt shifts inject high-frequency voltage ripples directly back into the main power supply line. Based on the dV/dt relationship, a decoupling capacitor placed between the power line and ground provides a path only for those rapid voltage changes. The high-frequency noise is shunted to ground, leaving the main DC supply line stable. Simultaneously, the capacitor acts as a local energy reservoir. If the main power supply sags, the capacitor discharges its stored energy to fill the gap before the microchip crashes. By shunting noise and filling voltage dips, these components translate the math of instantaneous rate change into total system stability. This dynamic scales up to larger systems. In AC to DC adapters, heavy filter capacitors charge on the peaks of erratic pulses and discharge slowly, smoothing out the signal into a flat DC line. In audio equipment, capacitors leverage their frequency-blocking nature to separate signals, directing high-pitched frequencies to tweeters while shunting low frequencies elsewhere. Because capacitors release energy much faster than chemical batteries, they provide the instantaneous burst of power required to fire intense camera flashes. This simple arrangement of conductors and insulators, governed by area, distance, and calculus, remains a foundational mechanism stabilizing modern technology.